Hello students, welcome back. Let us resume our discussion in section 1. Previously we completed up to 1.4. Basically we went through all essential trig identities. Of course, the definition starting from a circle of radius r centered at the origin, and the definition of trig functions is from the same circle diagram. It's not diagram, excuse me. Graph of circle and Pythagorean triangle and angle and so on. Okay, alright. Anyway, here are the definitions of all 6 trigonometric functions. And then reciprocal identities follow immediately from the definition. So there's basically nothing to prove here. Quotient identities is easy to prove, but the implication is significant, especially the first one, which I called formula number 2. And then what formula number 1? Here they are, put together as a single entity, the formula number 1. The Pythagorean identities. We proved the first 2, and then the third one is left as an exercise for you. Alright, so much for all the essentials. Now let's go ahead with some a little less important and a bit confusing identities. But we have to prove those somewhere at some point, and this is the right moment. First, symmetry identities. Sine of negative theta is negative sine of theta. Tangent of negative theta is negative tangent of theta. But cosine behaves differently. Cosine of negative theta is just cosine of theta. So sine and tangent are odd functions. Cosine is an even function. If you look at the graphs, then you can see the behavior clearly. Let's see. Sine function, symmetric with respect to the origin. Cosine function is symmetric with respect to the y-axis. X equals to 0, the vertical line. Tangent function is symmetric with respect to the origin. You can see those behaviors from the graphs, but if you have to prove it, then just looking at the graph will not be sufficient. You have to go back to the definition of the trigonometric functions, which came from a circle, unicircle, or circle of radius r, which I prefer. Okay, let's go ahead and prove those. Oh, by the way, a comment before starting the proof. Because of those sine, cosine of tangent behaving like this, the reciprocals, cosecant, secant, and cotangent follow the same behavior. And the latter part do not require proof. They follow immediately. So let's look at the standard 3 only. Sine, cosine, and tangent. Alright. Look at a pair of pictures here. First, angle theta. Second picture, angle negative theta. Do you see that? Counterclockwise, that's positive direction. Clockwise, that's negative direction. Let's run it again. We have different angles, maybe different quadrants, but the same. Counterclockwise, theta. Clockwise, that's negative theta. Now we want sine of negative theta. Okay, all right. What is sine of negative theta? Which picture do I have to look at? Well, negative theta is coming from the second picture. Angle is negative, clockwise. So that's what we have to look at. And then sine is y over r. Makes sense? Let's make it a little bit bigger. And then let's see, first picture and second picture, I'll be confusing. So let me label that. So y2 here over r. R stay the same. And then is coming from the second picture. All right. Let me color code red. Now, how do these quantities correspond to the first picture? This y-coordinate here from the second picture and this y-coordinate here from the first picture have the same magnitude but opposite direction. So this is actually negative of y1 over r. And now back to the first picture. Remember, y2 and y1 have opposite sign. One's going down, one's going up, because we are looking at the symmetry with respect to the x-axis. Counterclockwise versus clockwise, all right? So this is basically negative of y1 over r. And what is y1 over r? Y over r here in the first picture, here, that's sine. And we took negative out, so this is negative sine of theta. So we want sine of negative theta, so we have to start from vertical over radius from the second picture, highlighted in red. But we have to express it in terms of sine of theta, so you have to bring it back to the first picture. And this y-coordinate here, this y-coordinate of the second picture, which I named as y2, and this y-coordinate here, the y-coordinate of the first picture, which I named y1, they have opposite signs. Now, can you do the same to cosine? Stop the playback and try. Well, if you do the same thing to cosine, this is what you're going to get. So cosine of theta from second picture, we have to look at the second x-coordinate of the second picture, x2 over r. But what is this x? In the first picture is same as previous x-coordinate. Same x-coordinate. This x2 and x1 are the same. So no negative, so we just get cosine of theta. All right? Previously, sine of negative theta, so you have to look at red graph, red picture, in y2 over r from red. And how does that work to the y-coordinate of the first picture is negative y1 over r, y2 and y1 have opposite signs. So after taking negative out, we have negative of sine of theta. Can you do the same thing to tangent? Well, go ahead and do that. If you do it right, you're going to get this. Again, from the second picture, and y-coordinate over x-coordinate of the second picture, red. And then how do they translate into x-coordinate and y-coordinate of the first picture? Turns out negative of y1 over x1, so that's negative tangent of theta. So I color coded. This red means those coordinates are coming from the second picture highlighted in red. Now blue, now those quantities corresponding to the first picture. Alright, we proved it for sine, cosine, and also tangent. And the other three, well, those are standard. Okay, enough time for rotation identities? I guess not. We'll stop here and then we'll consider rotation identities in a separate video, or maybe two.